Okay, let's turn to page 348. Now we are going to solve one problem dealing with coaxial cable. So if you can see from the diagram given to us, this coaxial cable consists of two main parts. The first one, we have the inner conductor with radius of A, and also we have the outer conductor with radius B to C, right? So in between here we have some material given as mu r equal to 2. It means that this is not the free space, it's something material in between. So now we are going to calculate the magnetic flux that passing through a region defined as here, the R, which is more than A, and then the Z from 0 to 1. 0 to 1. That's our surface of interest given by the equation. So we know that, guys, from this diagram, since the R given as between A and B, so by right we know that this is our regions of interest between the inner and the outer conductor, right? So that's going to be our surface of interest. So again, we assume that the length of the cable L actually much longer than the radius of C here, so which we can simply use the ACL to calculate the H field that propagate within these regions of interest. Alright, so that's our assumption, the length much longer than the radius. So now applying ACL as shown here, close integrations, the H dot dl equal to the I enclosed. Right, guys, so to apply this ACL, we need to draw our Amperian loop, which must obey two conditions. The first one, it must pass through the point of interest, and then it must completely close. So it means that we have to choose our point of interest within this region. So let's say this is my point of interest located at R radius. The R could be any value between A and B. So now let's draw the Amperian loop. As mentioned just now, we must pass through the point of interest, and second one must completely close. Alright, so that's our Amperian loop. So now from this equation we know that, guys, this left hand side refers to your Amperian loop showing here, right? So from there we can find the H equal times 2 pi r, right, guys? This dl refers to the circumference of the loop, right? And now we have to find the I enclosed. So if you see closely from this diagram, within this Amperian loop, the only I that exists is actually the I that flowing within the inner conductor, which is flowing in positive Z directions, isn't it? So that's the only current that exists within this loop. So we can simply put this right hand side equation become the positive I. Why? Because the I here flowing actually in positive Z, and then that's the only I that exists within this Amperian loop. So we have the I over there. So now we can find the H, finally, I over 2 pi r, and we know that, guys, the H now actually in phi directions. We can simply put a vector and put the directions of phi, ampere per meter. So that's the H field that actually propagate within the regions of interest, and the H now actually flowing in positive phi directions. Now we're done for that. So now let's look at the equation that we can use to find the magnetic flux given previously. Magnetic flux actually a B dot ds. Okay, guys, So the B can be obtained from the H by multiplying with mu r given as 2 over here. And the S here, guys, actually the surface that the flux pass through. So if I want to draw the cross-section view, so let's say I cut this cable, say I cut this cable in the middle, right? So I want to show you the cross-section view of this coaxial cable. So you will see that the inner conductor will have this diameter, right? This, let's say your center. So that is your A radius, right? And then the outer conductor here, whereby this is your B, and then here the last one is your C radius, right? So that's actually the cross-section view of this coaxial cable. So now we are going to find the surface of interest which defined earlier between A and B and the Z from 0 to 1. So let's say this is the area. Okay, this is the area. So this is the Z equal to 0, and this is the Z equal to 1, and then this is the R equal to A and R equal to B. So by right, guys, this is our surface of interest, the surface that the flux will pass through, right? So again, so let's proceed from this equation. We know that, guys, this ds can be replaced by the phi, and then the area here should dr times dz. So just put here dr dz, right? So again, next let's proceed to find the magnetic flux, and now substitute all the B value which obtained from here to mu naught I over 2 pi r, now in phi directions for the B, and then a dot with the ds obtained earlier, again in phi directions, now ds equal to dr dz. Okay, guys, so let's substitute all the limit for the dz and also for the r, the dz from 0 to 1, the r from A to B, right? So finally, can I have here these expressions of magnetic flux given as mu naught I over pi, now integrations 1 over r, dr integrations dz from 0 to 1, the r from A to B. So finally, your magnetic flux that actually passed through that surface of interest given as mu naught I over pi. Now we have ln B over A1. So that's our magnetic flux. Okay, guys? So I hope you can try yourself and make sure you understand the process of on how to find the magnetic flux, right? So I would like to remind you the surface here, actually, guys, the surface that the B passed through. So we don't care about the other surface, so just concern or care about the surface that the B passed through, right? So since the B here actually in phi directions, so by right the ds also will also in phi directions. Okay, guys, so I hope you can try yourself and good luck. All the best.